Now we come to the last two topics. The first one in this lecture will be boring logs and field data and how they're interpreted. In putting this section is the newest section. I guess I've never actually done one like this before. And it's kind of, and I found out sort of why. There are several things I want to make mention of about this topic. The first one is that your Soils and Foundations Reference Manual does a better job of covering this topic than anything else, and by any place else. Most soil mechanics and foundations textbooks really don't do this topic justice. It's an important topic, however, because many times people will think, well, if they don't go into geotech, they'll never bother with these, and that's true to some extent. And it doesn't have the theoretical pizzazz that a lot of other topics do. But interpreting soil borings is central not only to the practice of a geotechnical engineer, but it also requires the geotechnical engineer or the engineer who's using them to basically put it together, to basically take all these little pieces of knowledge that they've acquired both in academia and afterwards to actually make that knowledge useful. And they're the link between what we learned before and what actually comes in actual practice. As a result, it's a good way of aggregating our knowledge of what we're doing in geotechnical engineering. And as a result, it's an important topic. It's one that needs more attention than it gets. The first slide I want to look at is this interesting looking advertisement. This actually shows how a Jeep basically was used in the upper corner, but as this is your classic cathead SPT rig, where you've got the weight in the middle and it's being pulled up and down. Actually, the winch is on the backside of the Jeep. Willys was the company that actually produced the Jeep in the first place. It was produced in World War II, and it's since passed through. It was part of American Motors, then it was part of Chrysler, and then now it's Chrysler Jeep, and then Fiat, all this stuff, all the acquisitions, but the Jeep line remains. And that's one of the early uses of them. This was actually, it's interesting to note that this particular advertisement show is used by the Raymond Concrete Pile Company. Raymond was it had what we call vertical integration, in that they did everything from the testing on the one end to the installation on the other. They were totally vertically integrated, something you don't see much of anymore in any kind of engineering practice, or ain't much of anything really. So this is an interesting look at that, both in terms of the history of an important vehicle and in terms of geotechnical testing as well. Boring logs are at the center of geotechnical foundation design. Without them, we don't do geotechnical foundation design. Without an adequate testing program, we are forced to guess at the type of configuration of foundations, which is one reason why we don't design foundations without them. This test section is going to center on boring logs. There are other important sources of information. There's laboratory tests, which are actually they're usually in many geotech reports, especially these days, they're normally presented together. You've got boring logs, and then you've got lab tests. And the lab tests reference the place in the boring logs where they're taken from. Those of you who saw some of my test problems are based on data taken in this way. And laboratory. So you can't really separate the two. And the kind of test that we do in conjunction with boring logs is interesting. Some of them are disturbed, some of them are undisturbed. Most of them are disturbed. If you can do it with a disturbed test and get what you want, that's the way to do it. We've talked about that in soil mechanics. Geophysical methods. I wish I had more time to really discuss geophysical methods. Ground penetrating radar and sonic methods and all that, electrical resistivity methods. I kind of touched on those in soil mechanics. Those are becoming more and more important. They are another import of the oil industry, which went a lot deeper than we normally do in geotech. But they're important from the standpoint of they are able, some people have thought, well, if we do geophysical methods, we can pretty much dispense with boring logs. That's not true. The two are actually complementary to each other. Geophysical methods are good at giving us a good broad overview of what a site looks like. They can tell you where the component layer is. In topographies like target topography, they're especially useful in finding voids, which can be, they can give you a lot of data over a wide area, and they can help you if you do your geophysical methods first in actually narrowing down what you want to see in your boring test program. So they're very much complementary. They give us two views of a site that enable us to get a complete picture of it. The third is site plans. The site plan is part of boring. Particularly, like I said, if we were blessed enough to have a geophysical program to start, we could actually, where we want, take borings. We're going to talk about that. And that's an interesting topic. We're going to actually touch on that. And data from tests such as CPT logs. I want to talk about, that's actually a form of a boring log, but it's different from what we normally do. And we talked about how these are taken in soil mechanics, and it's covered in your book very well. And of course, we had the infamous boring video. And so we had to, so now we have we have CPT as another one. And in fact, on some sites, you will actually see conventional boring logs and CPT data. The biggest drawback with CPT data, as I mentioned, is that you don't get a sample out of it. That's a major drawback with CPT, and I think it's one reason why we don't. That's one of the big pluses of SPT data, and that's one reason why we don't. CPT has not completely blown SPT out of the water. There are other reasons, but I think that's one of the major reasons why it hasn't. Okay, sample boring log. This is from your book, and we've gone over this kind of in a cursory way, but I want a bit more detail. At the top of any sample subsurface exploration log, which is the fancy term for boring log, you've got all kinds of information, the date of the project, its location. Many times, not here, but they'll give the latitude and longitude of the of the boring. They'll give the weather conditions. They'll have the type of testing equipment, for example, the type of SPT hammer that was used. They'll have in some cases, they'll put the location of the water table at the top rather than the boring log itself. And then we have along here a number of interesting, you've got the depth. Now, this is an important point. And in reading boring logs, you've got two datums that you have to consider when you're actually reading them. One of them is the depth from the surface, and one of them is the distance from some datum, be that datum sea level or whatever datum is being used. They're not the same. By far, they're not the same. And if we have a site with uneven surface, which all sites to some degree have uneven surface, just some are more uneven than others. Then you have to read your boring logs, or if you have a series of boring logs, you have to read them in terms of not just the depth from the surface, but where the surface actually is. And sometimes that takes a little digging on boring logs. Not all boring logs are really clear on that. And there are ways of getting around that problem. We'll look at them in a minute, but not all. You have to be careful. You know, this was from the depth to the surface and blah, blah, blah. Well, the question is, what's the elevation? And sometimes, for example, particularly with driven piles, they'll give you, well, tip elevation has to be such and such an elevation. Well, if you have a depth, you know, what's the elevation of the surface? How far down am I actually going with this thing? So sometimes the information you're given has to be pieced together. After that, we have the sample number. With the SPT particularly, we take samples as we go down, and we number those samples, and we bag those samples, and we get them ready for laboratory testing. And in some cases, the laboratory testing can be done in the field. Disturb testing in particular. And of course, obviously, the sooner you can do laboratory testing, the better. Not only for the convenience of the client, but actually so that the soil will reflect what's going on. So, you know, that's important. Then we have SPT, and there's notice here that there are 3 SPT blow counts. There's room for 4. Traditionally, with the SPT, you take the last 2 out. Each of these represent how many blows are in a 6-inch length. And traditionally, you take the last. You got 3 6-inch run lengths, and that's 18. You take the last. The blow count is the sum of the last 2. You're seeing more and more 4 6-inch runs being taken. You still take the last 2 for the blow count. And over here, last but not least, we have the actual how they interpret the SPT. Some boring logs will just let you do all the math. This one does it for you. And then you've got other. Then you've got a description of the soil. Most boring logs today, not all of them, and we're going to see some exceptions to this, give the soil classification. Traditionally, boring logs have given a description like this one of the soil. And the geotech is supposed to take that description and use that for design purposes. In the past, that the verbal description, which we talked about in soil mechanics, appears there. But today, it's almost normal to have a soil classification, 2 letters. Usually it's a unified soil classification there. So that's normal. Moisture content, not all boring logs have that, but it's definitely something you see on quite a few of them. In fact, the fact of the matter is, that's another thing. Boring logs there's no rigid standard to their preparation that applies across the board. Now, I know there are probably standards out there how to do it, but if you're involved with a single agency, for example, like a DOT or the Corps, you will have a certain standard to which you're expected to do this, and you will have it in a certain format, you have certain information on it, and that's very nice. In the Corps case, interestingly enough, different regions will have different, a little bit different specs. But, and that's not unusual. You have different soil conditions, but there's not a uniform. You don't get the same information on all boring logs, especially if you are in a position like you're for a contractor where you do work for different entities. You're going to have to be, and different geotech firms prepare these things. You better be prepared to look and see what you actually have. I will make mention of the fact that most all geotech boring logs today are prepared using a computer. Virtually all of them. In the past we hand drew all this stuff, and you'll see that in the older books and some of my older material. But today it's all done by a computer. One important note over here at the end, when we get past all the sandy gravel and the silty clay and all that good stuff, we hit rock. And we have a description of the rock, and then we have its RQD. RQD is very common on borings which involve rock, which is a major reason why I like to see students run the test when I'm teaching soil mechanics laboratory. It's an important test. It's probably the single most useful test we have to classify and quantify what a certain sample of rock is all about. Sample boring log. This comes from the core, and you will see that in addition to the SPT data coming down. Now this is interesting because we have two boring logs. We have two, and this is not unusual. The core is very good for this. You have two different boring logs. You have them on the same page. You have them against this elevation, against a certain dam. So you can see that this elevation at the top and this one is not the same. So that was what I was talking about there. You've got all your nice little unified codes here all the way down. In some cases you've got a hatching code for those. You have SPT data all the way down, and in fact it's actually done for you. This is it's actually all aggregated. They don't make you do all the addition and all that. The one thing that you must be careful about with SPT data, particularly these days, is the fact that most SPT is done, and the boring log should indicate that. They don't always do. But the boring log should indicate that the SPT data is taken with either most of today's hydraulic hammer. That's pretty much displaced that cat head like you saw in that old photo. And that obviously influences the fact that you have to correct whatever efficiency you think the hydraulic hammer is back to N60. In some cases, the boring logs will actually do that correction for you, because virtually all the SPT correlations we have are based on N60, even though most of your hydraulic hammer, 89%, is pretty typical. You also have the moisture content, like we saw in the other one. We also have, and if you, by the way, that would also indicate if you have the moisture content. If you've got a decent idea about what the specific gravity might be, which it's pretty narrow range, you could actually, if it's below the water table and you have reason to believe it's saturated, you compute the unit, you back compute the unit weight. It is very seldom that a boring log, you'll see it occasionally, but most boring logs do not have a unit weight on them. And then we have liquid limits and plastic limits. These are very common with soil boring logs to use Atterberg limits because they're undisturbed. They do not require a disturbed sample, and you just get an enormous amount of information out of them. And last but not least, we've got long description. In some cases, these are long. And in fact, this case, you've got from 22.1 to 50 feet. You've got this and this. You've got actually your layers in terms of elevation from the depth from the surface. Excuse me, not elevation. The thickness of the layer, and then you've got elevation from the surface down. That's kind of handy. On boring logs like this, you have to see what this is. This elevation is, and then you have that, and then that's how you do your layer. By the way, just as an aside, most of you, we've talked about layered stratigraphies, and that's pretty much standard in geotech. But, layered, most of the time, your boring logs pretty much tell you how to layer the thing. And the only layer you have to add, at least from just a strict standpoint, is where the water table is. That would split a layer. So that's that's an important that's how we figure out how to layer it. Now, in some cases, if the SPT data in a layer varies quite a bit, and quite a bit, of course, is a matter of experience. If the SPT layers, when you actually sit down and do the analysis for the foundation or whatever you're doing, you probably need to split this up, say, in a couple, split that up. There's a boring log key. The Corps is very good for putting these on in their documents, boring log keys, and they in general notes, they're important. So given the non-uniformity of soil boring information, you need to know this. A couple of other boring logs. This one is from Ohio. Ohio is the only state that I know, and there may be others, that uses the AASHTO system for their classifications in their boring logs. Most of the time, AASHTO classifications are restricted to pavement issues, but Ohio uses it in their on their boring logs, and you can actually see it right over here, along with some of the other data that is very common. The next one over here is kind of sparse. It's from a small project near Atlanta, and it shows you, again, it has open air under bridge, which means there's nothing. This isn't. This is one situation where the depth is actually not the surface of the soil. It just isn't. But and with overpasses, that's very much, particularly if you've excavated the roadway under that, or whatever's going under it, railroad, whatever, the overpass, that's pretty much the case. So you have open air under bridge, and then an alluvium. You got a creek in there somewhere, and then you've got go right into partially weathered rock. This is a fairly sparse. It does have the elevation on it. It has, in addition to N values, which are also very sparse, it has blow counts as well, SPT blow counts, and it has provisions for plastic and liquid limits and moist, but it does not contain them. Some boring logs are very sparse in that regard. Sometimes this is okay, sometimes it's not okay. Sometimes it can be very exasperating. This is another core. You'll notice here that this is done a little differently in that, first of all, they have this hatching code. You'll see this on some boring logs require that you have a hatching code for different types of soils and different hatching patterns. And that's interesting. But they also have in the same one all of your you've still got your two-letter unified codes. You have other little notes here which are abbreviations for certain things. Then you've got the water content here. You have water content percent water content. You have your shear strength. There's a couple, for clays. This is particularly true for clays, and there's two ways of getting this kind of data. One of them would be to take undisturbed samples and do unconfined compression test on them, which you see sometimes, but the more common way you're seeing is doing vein shear tests. Vein shear tests are becoming, you see more of them than you used to. They've come of age. It's a good in situ test where you can actually get the results without having to dig through a bunch of, without having to get the thing out of the ground, hope it stays undisturbed. It also has wet density. This is rare that you will see that on a boring log, to be honest with you. But as I said, but occasionally you will. And then normal stress in tons. It's also rare to see, but the wet density would enable you to have a really good effective stress profile. But again, that you don't see that in all of them. Information, this is sort of an overview, and we've kind of gone through all this. There are other types of data. Boring data is not the only game in town. You also have test pits for very shallow foundations, and for work, test pits are fine. In fact, you get your best, definitely get your best sampling out of a test pit, both just undisturbed, disturbed, and certainly undisturbed samples. Your best are your test pits, or hand augering. Hand augering is something that is more associated with stuff like the USDA did, the soil surveys for agricultural purposes. Occasionally you'll see it in geotech. And CPT, but it can be useful as well. Particularly, that particular type of data is important, especially environmental considerations. And CPT test, where they're boring, but the data is entirely different. And in fact, in some cases, you will be, some particularly critical projects, you will be able to have both the CPT data and the boring data from the same, they'll be in different places, but they're still, they complement each other. For very good project, that's really an ideal way to see if you can get both that, and then you've got a very complete picture of what a job site looks like. Of course, with CPT data, you can classify soils. That's a little. There's a little bit more to that than we went through in soil mechanics. We just covered the basics of it, and there's more than one way to do it. But that partially makes up for the fact that you do not get a sample out of a CPT test. Site plans. Boring logs are not very useful unless you know where they are with respect to what you're trying to build. And that's what a site plan is for. The boring logs are, to be honest with you, of course, on some projects I've looked at, I say, where's the site plan? They tell me, well, there's not much of a site, so we don't have one. But that's not really a very satisfactory state of affairs. What you really need to know is that where your borings are, because if you've got, for example, if one side of the overpass is radically different from the other side of the overpass geologically, you need to know that, because you may have a whole different foundation situation on one side than the other, and that's important to know. The site plan gives you, and you'll also notice that this particular site plan, which is most of this is in the back of your book in Appendix A, the Apple Freeway project, which is an interesting exercise in and of itself. We're going to talk about some of it. You'll notice that both the CPT locations and the conventional borings are shown, and they're close to each other, and between the two of them, again, you can get a very complete picture. Before boring sources of site data, anytime you set out to characterize a site, before you specify a test program, if you're the person to do that, you need to find out what information you have, and that information changes all. We have a lot of, there are major, there's continual change in the way that we gather data, and stuff which we taught, say, even 10 years ago is obsolete. So this list is a guide to you of what you can do. One very useful thing that has not changed, there's boring logs from previous projects, if you're doing a project redevelopment or a site an upgrade, if you have those information, use it. That's really, but you've got other things, aerial or satellite or Google Earth, that can be very useful. Although Google Earth misses stuff too. Don't just look at Google Earth and says, declare victory. You've got some geophysical stuff that you can use, maps, existing maps. There's the soil survey is what the USD is what I was talking about with the augering. These are just, like I said, many of these lists most of the lists you see in books are out of date. There's new information out there. You should take advantage of it, whatever you can find. I've noticed that in some of my in some of the design projects I've seen where I've given people actual site data and they've gone to Google Earth and found out more about it, and that's good. That's good. That shows that people are interested in what's going on, and they're taking a more proactive position, which is part of the reason, which is part of my objective, really, is to get people to take a more proactive approach to their work. Field reconnaissance. It's always pays to visit a site, particularly if it's major. It's very, you can with your own eyes and ears see stuff that all of the virtual data you get doesn't show you. For important things, it's important to do a site reconnaissance, and the more site reconnaissance you do, the more obviously the more you've prepared for it by taking the data you have, the more valuable the site. So well, I'll just go out there and look at it. Well, if you haven't, if it's just a cold thing, well, that's your data is going to be limited, severely limited. But if you've got some information going in, you know what to look for, and that's important. And of course, you can record structures and that kind of thing. Once you've done your preliminary investigations as a geotech, then you actually specify the subsurface exploration program, and that program is based upon a lot of things: the size of the project, how critical it is, how good, bad, or indifferent you think that the geology is for building stuff on top of it. It's getting easier. It's many, like for example, if you're for some entities like particularly your government, they've got very specific expectations of what they want to see in the site exploration program. That's not, by the way, that's not always, if you feel you need to recommend extra, you need to do that. Because just because their specs say, well, we've always done it this way, and this is the way we're going to do it, doesn't mean necessarily that will discover what you want. And the more you information, it's a chicken. The whole geotech is kind of a chicken and egg thing, where the more you know going in, the more intelligent a exploration program you can design, and then design is a good way is a good way. It's part of the design process. This is a guidelines for the minimum number of exploration points. This is a guideline. These are not always easy to come by. Different agencies again have different specs for these. This is a good to find out how many borings do you really want. One of the reasons why I generally tend to lean towards AASHTO type of specification is that most of your DOT specifications tend to be are usually conservative and reliable in their, and that's why I emphasize them so heavily. In private work, you get into all kinds of variations. Sometimes, and sometimes DOT stuff is overkill, but it's better in geotech. It's better, a little overkill, particularly at this stage of the process. A little overkill is definitely better than inadequate, because inadequate forces the designer to guess what he or she is going to do in terms of a foundation or retaining structures, and then the costs start going up. So DOT specifications are always a good place to start. And like I said, private work, you get much more wide variations than that. One thing you noticed is that subsurface profile. The subsurface profile is an important way of, it's basically a cross section of the design. In other words, basically what they'll do is they'll take a few, 2 or 3 borings, sometimes more than that are quote unquote in a row, more or less in a row. And they'll actually put them side by side. They'll line their elevations up, and from there you can, and then very frequently once they get them in place, they will pick up the they'll show you soil profiles as they vary along, from one boring to the next. They'll show you that, and you can see that here. For example, the rock layer, the bottom rock layer, is going down in this direction, and that's obviously very important for your foundation, is to know where that trend is going. So, which means you probably will have longer foundations on one side of the overpass, or in this case overpass, and you will on the other. Or on a building where if you've got a rock layer, if your basic rock layer is going down from one end of a building to another, which is very common, then you're going to need different foundations on one end than the other. I remember when my family business built a plant expansion out off Amicola, and this was in the late 1970s. We had that. On one end, you could just go almost, do a little excavation and, a little rock breaking and set it up, and you'd have foundations. The other end, you needed to go down further with a deep foundation. So that happens all the time. And a subsurface profile, you can see this immediately. One trend you're seeing in boring logs, this one is from Arkansas actually, is that they will take the subsurface profile and aggregate it with whatever they're trying to put on top of it. And they have different borings here. This actually, they'll actually put the borings with the structure. You're seeing more and more creative ways of doing this because of the improvements in computer graphics, and you're also seeing to the point where the subsurface profiles are so detailed they don't need the main boring log, and frequently they'll dispense with it. So you're seeing a lot. Again, changes are constant in this business. The idea, once you get to boring logs, you want to actually do something you can do design with. And the ideal for most of our work would be to have profiles with different nice little soil layers and whatnot. And by the way, in many cases, if you've got wide site variations, you'll need more than one profile. This part of the job, for example, may have a different profile than this. And we've seen what one example that was with the rock layer. But ideally, what we'd really like to have for our more coulomb is a nice stratigraphy with every layer has the more coulomb triple associated with it: Phi, C, and gamma. Boring logs seldom give this information directly. Maybe this will change over time. Most data comes from disturbed samples, and therefore your empirical correlations are common. If you do get some undisturbed samples with them, that's fine. That's all the better. But most data from, for example, one type of undisturbed data that you will see, and depending on particularly your softer clays, are consolidation tests. which are associated with different parts of a job site. That's very useful. Empirical correlations are common in reducing boring log data. SPD data is still the most common type in spite of the problems with SPTs. CPT data has additional opportunities, and we're going to talk about how to apply that here in just a bit. Many times in the absence of anything else, let's maybe make that disclaimer right up front. If you've got other data that would take you in another, or use it. But you have different types of correlations. You have different correlations. I'll show 3 of them. This table, which we've used before, I've shown you this before, is probably the best known. It's the least reliable, but for preliminary work, it can be useful. If you get something a little more detailed, you might want to look at some of the correlations on the right side of the screen. And they need to be used with care. But for cohesionless soils, and cohesion soils are easier to do this with than cohesive soils, you get better results. Again, they need to be used with care and judgment. But infrequently, when you're given boring data, that's all you have. That's particularly true if you, as the engineer, were not the person that designed the exploration program and took the boring log data. That's not all. That's sometimes we have some end-to-end control over it, and we did the boring log, then we got this data which was what we wanted, then we use that data, and blah blah blah. And that's all wonderful if that's your position. Sometimes you're just handed something and said, "This is what we've got." Don't be afraid in situations like that to use disclaimers, because you don't need to let what you don't what you don't know and you can't know from the data you've been handed just simply pass by. Use disclaimers. Be clear about what you don't know, obviously based on the best observations. Correlations for cohesion. By the way, your book has a nice little section towards the end about how to prepare a geotech report. I'm not going to go into that, but it does have that. For cohesive soils, it's kind of more of a, it's not, cohesive soils vary in their properties even when their SPT data comes up. They are not as reliable. One thing that will make, as I mentioned, that will really bring cohesive data up to par, or if you've got truly cohesive soils, is vein shear test and unconfined compression test. If you have those, that will make up for a lot of missing problems with cohesive soil data. Let's look at an example from the Apple Freeway project, which is in Appendix A, the boring UDH-BAF-4. We're going to use that as our reference boring. Find the idealized soil profile, the P0 diagram, the pre-consolidation pressures and consolidation process. The example presents many of the tests as coming from laboratory tests, and you do see that with boring logs. We're going to also look at this as common. We'll attempt to correlate these methods by other means. It's not going to be a perfect process, and you're going to see that there are variations, but that's pretty much normal. Let's look at UDH-BAF-4. The first thing it has, and I'll highlight some data on this. The first is the water table. You'll notice that one of the interesting things about this boring is that it has a history. You don't usually, most of the time, water table data is a snapshot, one point in time. Water tables are constantly changing. How much depends a lot on the location. You have drought conditions, you have flood, you have rain overage conditions, flood conditions. It's going to change. And as we've seen, that can have a drastic effect on effective stresses and a lot of other things in soils. If they're expansive soils, that's definitely a big issue. And as a result, that's a nice thing to have, but it doesn't always, you don't see it very often. The SPT results, I've talked about those. Vein shear test. They actually took vein shear tests, and this is becoming more and more common with borings and cohesive soils. Undisturbed samples for laboratory tests. You'll notice that they took push tubes and got their nice undisturbed samples out of those in conjunction with the vein shear test. So you've got a kind of a belt and suspenders approach here. And last but not least, as I pointed out before, the Rqd test. And there are we're going to talk about 3 layers here. We're going to go down to, we're not going to go all the way down. We're going to go down to a certain depth, and we're going to talk about the first 3 layers. And the layers correspond with this, and then we have the this and then that. We're going to talk about the top 3 layers of this thing. You obviously want to have your borings need to be, one of the important things in designing a test boring program is you need to anticipate how deep you want it to make sure that whatever foundation you specify for it, you've got data for it. You do not want to put a foundation blindly into below the bottom of your explorations. Now, from what we've seen with the soil boring logs, we can construct an ideal ISO profile based on the boundaries that they have. We're going to talk about the first 3 layers. Layer 1 is the black organic silt layer. We assume it's unsaturated, not necessarily dry, but unsaturated because it's above the water table. And assume the SPT values are N60 corrected, which isn't always the case. N60 is equal to 1 plus 1 is equal to 2. It's very soft soil. Our correlations figure about 100 PCF, so 90 PCF is reasonable, which is what they use. Layer 2, the water table, you have to split it. Basically, it's kind of 2A and 2B kind of layering. The N60 is 17. Unit weight would be about 110 to 130, given at the lower range. And then they pick the lower range. Layer 3 has no SPT data. We have vein shear data, however, that the cohesion is 1050 to 1250 PSF. That indicates a stiff soil, maybe unit weight 120, 140, so they picked 125. I'm showing you how I would pick the unit weights based on, on the information that I have. They have another method. There's a lot of judgment involved here. Submerged unit weight, this is the one place I'm really not sure why they did what they did. They picked it using an intuitive process. There are 2 ways, strict ways we've learned to do it. One of them is to take the saturated unit weight and divide by 2, and the other one is to take the saturated unit weight and subtract the unit weight of water. They've not really done either one. The results are a little different. So they take an effective stress diagram, they construct an effective stress, and we're going to construct it based upon the unit weights that they have. Up until the water table, they're the same, of course. There's total stresses. You have no, your total stresses are the same. You use your total unit weight. They actually, what they actually do is this is a submerged unit weight type of diagram where they kind of massage the way that they pick the submerged unit weight. Is where this is done. But then they have, but then they turn around and they create a total stress, effective stress P0 diagram, as you see here. So they kind of do it a little differently. Usually, if you've got a diagram like this, you take the total stresses and you subtract the pore water pressure, and you get the effective stresses. They construct a total stress diagram based upon the full unit weights. Then they subtract an effective stress diagram based on the submerged unit weights that they have specified. And they show you how, using detailed calculations, how they actually come up with it. And those are very useful for those of you who are still still trying to perfect your technique on computing effective stresses. And that's how they do the effective stress diagram. The direct shear test results are down there in the corner, and they show those particular tests are from Rqd Test, which means that they did them in the laboratory. They also actually, this is a fairly extensive laboratory testing procedure where they actually give you remolded and so this is a fairly comprehensive study using, like I said, they've used both they used both the undisturbed samples for their laboratory test and vane shear test. That's a good way of kind of cross-checking to see if your disturbance is really an issue here. Consolidation data, you can, if you don't have laboratory tests, your Atterberg data, as we've seen, will allow you to compute your coefficient, your consolidation and your settlement coefficients. If you do have that data, you're much better off if you do. One final thing I want to mention is that once you've got this data, you can actually take it and use it to estimate the your pile ultimate capacity. And this is an example of that using Splenius' method. It's fairly straightforward. Because you've got most of your data from you start mostly in this case with the type of soil, and that effective stress diagram pretty much give you what you need to know. First the square, you compute these across either the wetted area around the perimeter times the length of it. It's a 12-inch, so it's 4 feet around, times whatever length of the section is. You get that number of square feet. The effective stress in the middle of the layer, which is the average of the top of the layer and the bottom of the layer. And I'm not going to go through that in detail either. And then you compute your beta based upon the Splenius' data that he get. We talked about that way back in driven piles. And then all you do is multiply those three together, and you get the Q for each individual layer. We actually ignore the top layer, pretty much, as a soft, and we talked about why we do stuff like that earlier. And we end up, and then at the toe, you've got the effective stress at the toe, you've got the square cross-section layer, a 12-inch square has a cross-section area of 1 square foot, and then you multiply it by your the effective stress at the toe times the beta there, and that gives you that, and then you add it up to about 143.4 kips. So that's so you can see how, and that's one of the reasons why. And again, Splenius' method is simple because you're not worried about a lot of the, once you conduct you know what kind of soils you have, and you know what your effective, your geometry is. In fact, you pretty much have it. So CPT method, although it doesn't need to be pushed too hard, and I'm sorry about that. The analogy between a driven pile going in the ground and a CPT program has simulated direct application of CPT data. There are a number of methods that are in use today. One of them is Schmertman designed one of them. That was one of the things that the government sent him to do, and his methods are popular. I'm going to use that of the Islamian Splenius. It's a little simpler to implement, and it's a little easier. And it's also a well-accepted method as well. Okay. Basically, the Islamian Splenius method. Now, again, all methods like this for deep foundations, whether it be driven piles or driven shafts, are all pretty much the same. You have to first compute the unit shaft resistance and the unit toe resistance. And then you multiply that by the area, which either the end area on the toe or the wetted area, the perimeter times the length of the layer, and you get a capacity in kips or kilonewtons for the cross section for the shaft areas. You add them up, and then you add the toe area. You get the total. It's no different. Just because I'm suddenly using CPT data directly doesn't mean that the game suddenly completely changes. It doesn't. We have the toe. We start with the toe resistance, which is simply equal to his toe correlation coefficient, which is this is from Splenius' own documentation, so it's equal to usually unity, but if you get large enough piles, then you have to use these times this QFG, and this is where things really get kind of exciting. The geometric area, the cone stress area, the geometric average of the cone stress area over the influence zone after correction for pore pressures of the shoulder and adjustment for effective stresses. Sometimes that adjustment is easier said than done. The cone stresses are if you recall, when you push a cone in the ground, you've got resistance along the side, the F of S, and the Q at the toe. That's what we're talking about here. And correcting it for poor water effects is very important. Something that gets overlooked in CPT analysis. And Splenius' book, which is either available in print from Pilebuck or on my website, is one of the best references I can think of for that particular topic. There are several topics that he covers better than just about anybody. That's one of them. Another one is the case method in pile dynamics. He covers that about better than anybody either. So, the shaft resistance is another one of his shaft correlation coefficients, which is a function of the soil type. And those are given on the next page right here. And this is QE, which is cone stress, again, after correction for poor water pressure on the cone shoulder, and adjustment for the apparent effective stress. It's similar, but not exactly the same as the toe. Notice that he uses the cone stress at the tip of it in both cases. He doesn't use the friction, cone friction, which is an interesting way of doing it. But in any event, that's the way in which that's his method, and that's it. The tricky part of it is making sure that you have you take into account poor water effects and those and effective stresses. The effective stresses are fairly easy. Other effects may not be available to you. Let's give an example. Profile shown below: 12-inch concrete pile, 45-foot long ground line, ultimate static capacity using the E and F method. Our pile configuration is pretty conventional. We have 4-foot perimeter, 12-inch times 4 is 4 foot. Toe area 1 square foot, and then the toe correlation coefficient we'll just assume to be unity. Layering. The layering is taken from the CPT data, not from the other one. So we have it has its own layering structure. Layering, first layer we're going to lay soft soils. The second layer is sands. The third layering are other types of soils, and we're going to, and each of them have 5 items. They're all the same. The first one is QT, the cone resistance. The cone resistance comes from this. Now, you know, we have to do a little eyeballing to get some of those, but if you had better, had direct access to the cone data, you would have better, you would have a better number for those. So that's number 1. Okay, the second one is the U2 above the water table. Now, it's interesting to note that over here is the U, and that's in feet. Now, that's interesting, U in feet. Where have we seen that before? If we go back to permeability, and you go back to beyond permeability to other types of, even in my fluid mechanics lab where we talk about head, that's what you're looking at. The U is in head, in feet of head. It's not in PSF. So keep that in mind. That's what we talk about. The U2 is 13 feet of head. And we're basically taking that off of the of this. Now you'll notice that the broken line here is the hydrostatic case. In other words, 0 head at the water table, and then it goes up. Actually, it's a direct, function. The head is direct function of the depth. In other words, if you've got 20 feet of depth, you got 20 feet of head hydrostatically. Up until about here, which is about about 28 feet, they pretty much follow each other. Then you've got this. This is important because sometimes soil profiles, we always talked about, hydrostatic head is always our default assumption, but as you see here, sometimes it doesn't work out that way. That's why you have down here 125 feet. That's not 125 feet. That's 125. Your cone is telling you there's 125 feet of head, of hydrostatic head at that depth in that layer. The third one is the adjusted cone pressure, which is basically the cone pressure minus the whatever head. Whatever water pressure, is there, because we actually have to convert our heads into pressures to use it that way. Number 4 is the shaft coefficient based on this table right here. And number 5, you just simply take the C sub S, you multiply that by the Q by the Q sub V, and voila. You get the RS, which is actually the same as the FS in the conventional Splenius method and in the O'Neill and Reese method for drill shafts. Just a little notation difference. At the pile toe, we don't have the effective stress data. What we'll use is Q sub V is equal to 32.2 KSF, which the RT is simply 1 times that is 32.2 KSF, which should be the Q or QT for the other one. So it's a little bit different notation. So all we do is we apply these. Once we've got these 2 unit resistances along the shaft, along the toe, we simply multiply those by the areas, and we come out with 204.52 kips for the shaft, 32.2 kips for the toe, since it's a 1 square 1 foot squared cross-sectional area, add them together, 236.7 kips. And that's how you apply. The reason why I bring that up is because we are seeing more and more CPT data being used particularly in deep foundation design, instead of going through the process of finding the more Coulomb triple. We actually use the CPT data that we have, and we use it to, and there are problems with that. CPT data is not something to be used blindly, but that is the trend in deep foundation design, is increasingly to use CPT data for that purpose. So that concludes this topic. Until next time, thanks for watching, and God bless.